So this talk is called All This Useless Beauty. It's about surreal numbers in JavaScript. So it's kind of a tricky topic and it's not particularly useful. It's nice to get this over with so we can get on with actual useful stuff that will make you better developers for the rest of the day. As Jared mentioned, I'm a teacher. So this is the kind of thing I try and get my students interested in rather than just how to make money doing web stuff. I'm not really a social media kind of guy, but you can find me on Snapchat. My username is Crodhead. And I'm also Coldhead on IRC if any of you ever run into me there. And I'm from Sydney. So these slides, obviously, this is just the plug for my sponsor here. This is Reveal.js. It doesn't look like usual Reveal.js, but I don't want you to think that I actually have design skills. I've actually ripped this design off from Jen Schiffer. I haven't even renamed the files. It's all still references to jQuery conference in Austin, Texas of last year. But I met her last year, and she's wonderful. She talks about the same kinds of things, except her stuff is much more beautiful, obviously. And I'd encourage you to go and look up some of her talks. What I have added to this is my own picture here, which is Harvey Birdman. There was a complaint from some people that I didn't include enough pictures in my slides. So I put Harvey Birdman on every single page there. And if you get bored, you can just look at Harvey Birdman. I like to think that he's kind of looking at my slides and quietly approving of them. So he gets a slide to himself there. This presentation contains one animated GIF. I know that you young developer people like animated GIFs, so I've got one in here. It's not a funny one, but if you're a fan of animated GIFs, you can look forward to that. So where do I come from? I'm not famous. I'm just one of the regular kind of guys that is interested in web stuff. I haven't ever done anything famous. I'm much older than all of you, at least spiritually. So I was doing this stuff last century, before most of you were born, before 9/11, I like to think of it. And I was making the internet, and it was all going fine. And then, I'm not exactly sure what happened, but something called the .com collapsed. And lots of people didn't have work for a while, so I went to university, and I thought, I'll study mathematics. That's got something to do with computers, probably. And that stuff's really hard, and don't study mathematics. Don't let your children do it. I really regret having done that. I discovered towards the end of my 7-year failing first-year maths 4 times degree that jQuery is quite fun. So JavaScript's not my favorite language. You can beat me up for that later. But I really like the community. I like the community. I like JavaScript because of you people that come to things like this. I like the jQuery IRC channel. I like jQuery because it makes it easy for people to do cool stuff that they're excited about. So that got me back into the web, and I ended up teaching. So I worked for a number of years doing that, and it turned out that it's easier to teach people, if you can speak, easier to teach than actually make things, because I don't have deadlines. My students come to me and they say, the project's due on Friday, I'm not going to get this finished, and it's not my problem. I just say, good luck with that. So what I learned at university, this is a brief summary. Maths is really hard, and it's very impressive that some people are good at it. I'm not one of those people. I especially hate calculus. I didn't realize there was going to be so much. I should have seen that coming, but it's just one of those things. I especially hate infinitesimals, so I side with Bishop Berkeley. When calculus was kind of invented or discovered, we'll talk a bit more about that in a moment, he wrote a letter complaining that infinitesimals were offensive to God. So you guys know that with the area under a curve, you can work it out by taking an infinite number of infinitely small things, and they add up to the area under the curve. That makes me feel icky. I really don't like that. It doesn't make sense. I know it works, I'm happy that it works, but I don't want to have anything to do with it. So I'm with Berkeley that is horrible. And it turns out what I should have studied is these fields called the philosophy of mathematics or meta-mathematics. So that's the stuff about how maths works rather than actually having to deal with the nitty-gritty details. So the kinds of questions you get to talk about in the philosophy of mathematics. Do numbers exist? Is mathematics invented or discovered? Would we have mathematics if we didn't have people? How do written symbols capture mathematical truths? What the hell is truth? I took 2 long courses on what truth is. I still don't know, but it's an interesting question. More relevant is how well do computers model mathematics, and we'll talk about that in a little bit. And questions like, how does Gödel's incompleteness theorem affect our daily lives? I'm not sure that it does, but it's fun to think about. So what I try to teach, I'm teaching 3 months at a time, a full stack web development bootcamp kind of thing. That's all the rage these days. So I teach people how to make web stuff, the full stack, as they say. And you know, my motivation is that I'm trying to teach people to have the kinds of skills that I would hire them for. So if they showed up on day one, I'd be able to give them something to do, and they'd be able to do something useful for me. But beyond that, I take it as an opportunity to teach people about the joy of programming, because I really love this stuff. I got into computers when I was a kid, and I've never really had a wobble about what I do with my career. That's just worked out well for me. So I try and teach them stuff that, like, this isn't anything to do with money, this is just interesting or fun. So the things that I insist that they should know, the things I say, when you have some spare time, this is what you should go and look up. I think they should learn formal logic. I think there is not enough emphasis on formal logic in computer science courses, and I think it makes us stronger developers. It makes development more easily if you're able to understand reasoning, that kind of abstract thought. And I also think you should learn regular expressions, because everyone should learn regular expressions. I mean, obviously, especially developers, but I'm often shocked to discover that people who are senior to me in companies don't know regular expressions and come to me for help with them. What the hell is the matter with you people? These things will save you time. So, you know, I tell my students you need to learn regular expressions. Why I think formal logic matters in computing. So you guys know about Turing machines. You don't have to know how to make them, but you know what they are. The idea was that, you know, when Turing invented this, he was like, how would I automate the processes I go through when I'm trying to think through some problem? So it's like a machine that does the job that a mathematician or a logician's brain would do. So Turing machines are basically mechanical reasoners. They can do reasoning mechanically for you. And computers that we use today are practical Turing machines. We wouldn't have computers in this state if we hadn't had the concept of a Turing machine first. Computers are also formal systems, so if you're able to think about formal logic and formal systems, then that gives you a sense of what your computer's doing. And I like to think that a computer is a tiny, frantic robot logician trapped inside these machines. So if you think of them in those terms, it's easier to push them around. So this is about surreal numbers, but I'll give you a little bit of context for this. Numbers is really strange. And children understand this. You forget about it because you just get used to them. You can pay your bus fare or you pay your rent each month or whatever else you need to do. But when you explain what numbers are to children, they understand that numbers are quite strange. And I like to encourage people to go back to think about this and kind of be weirded out by numbers. So for example, does the number 7 exist? And if so, where is it? Is the number 7 in this room somewhere? Would the number 7 exist if people didn't exist? Does it depend on the physical universe in some way? It's an interesting, but you know, obviously we can use the number 7 whether or not we believe in it. It's not an important question, but it's an interesting one. Where did the number come from? Where's it going? What does it want? We're utterly reliant on numbers, but we don't really know what they are. And I mean, I've thought about this a lot, and I still don't know what they are. And most mathematicians, it turns out, don't want to talk about this. They just want to get on with it. They ask you to stop asking questions and please leave the university. But if you're in the philosophy department, they will agree with you that foundations of mathematics are still uncertain. So there's a quote from John von Neumann, he of the von Neumann architecture, which our machines today are using. Mathematics, you don't understand things, you just get used to them. And that's really true. We just get used to mathematics. We kind of ignore how weird it all is. So let's consider the number 144. In decimal, it's expressed with a 1 and a 4 and a 4. That's what it looks like in binary, and that's the JavaScript version, because JavaScript doesn't want to do binary as a literal. That's the octal version, and that's the hexadecimal version. So these things all represent the number that we call in decimal or base 10, 144. But they're not the actual number, okay? You've got to keep that in mind. They're just different representations of this thing, whatever it is, wherever it is, the number 144. And these are basically just symbols which behave like the number. They do the things that we expect the number 144 to do. It's greater than 100, it's divisible by 2, and so on. So numbers in JavaScript. I've put some JavaScript in here because that's why you guys are here, so it seemed like the right thing to do. Programs generally model numbers as collections of 1s and 0s. So you know that computers are really binary, that's what they're into. And JavaScript, as you know, uses the IEEE 754 double precision binary floating point format, which gives us most of the values we care about. So we can count lots and lots of integers, and we get some rough approximation of a bunch of decimals. So in JavaScript, this is what 144 looks like in the computer's memory. It's 64 bits, and there's a couple of little 1s in there, and then a whole bunch of 0s. And there's some problems with this, which are fairly famous problems. You'll have heard about these. So we have problems with overflow and underflow and precision. So to give you some examples. In JavaScript, this is the biggest number you can talk about or think about just using native JavaScript. So you can access number.maxValue and it will tell you what the biggest number is, and that's it. And it's a huge number, but if you ever needed a bigger number, you can't do it in JavaScript. We also have this problem. This is the integers. If you're just counting integers, as soon as you get up to this big old number here and add 1 to it, you just get the same number back, which is not a great thing for a language that's doing mathematics to do. That shouldn't be true, but it is in JavaScript. You'll also have heard about this one. 0.2 plus 0.1 doesn't give you 0.3, gives you 0.3 and a little tiny bit extra. So IEE 754 is an imperfect model. You can do a bunch of mathematics, but you can't do all of it. But it suffices. So can we model numbers in a different way? And it turns out that yes, we can. So let's talk about sets. This is a terrible pun, and I'm sorry for that. Fortunately, you're all too young to know what I'm talking about. So I've stolen Wikipedia's definition of what a set is here. They're very easy to understand. In mathematics, a set is a collection of distinct objects considered as an object in its own right. So we say that there's a thing that is a set. It's a collection of things. So sets are usually delimited with curly braces, like that. And for example, here's the set of positive primes less than 10. So that's 2, 3, 5, and 7. I've defined how to put the numbers into the set, and then I've actually gone ahead and dropped them straight in there. So here's some interesting sets. That doesn't just have to be math related. So there's the set of people in this room right at this moment. That's a valid set. That's a thing you can talk about, you can think about, you can reason about it. There's the set of Paul Irish. There's the set of odd integers, and that's an infinite set. There's infinitely many odd integers, and you can still put them in a set. You can have infinite sets. That's fine. There's the set of things that don't exist, which is also an infinite set, and it's a very big one, and I quite like thinking about it. The set of things that don't exist seems to be much, much, much bigger than the set of things that do exist. And you can have the set of odd numbers and the set of odd numbers and the set of even numbers. So sets can contain other sets. That's not a problem either. And we've got this concept called cardinality. So the cardinality of a set S is the number of members of S. So for example, if we have a set B which has 3 colors in it, blue, white, and red, then the cardinality of that set is 3. This is easy, right? You can teach this stuff to primary school kids. So cardinality, the interesting thing about it, why I care about it, is because we can use it as a source for natural numbers. It's a way of generating natural numbers. It's a place where numbers can be derived from. So the number 7, for example, you can say that that is the cardinality of all sets with 7 members. So if we want to say, does the number 7 exist, we can say, sure. You just take all of the sets that have exactly 7 members, and it's the cardinality of those sets. It's the number of things in them. And see, here's some headache-inducing sets, so just focus on Harvey Birdman if this is too much for you. These ones are the tricky ones that keep people awake at night. So we have the set of all sets. That is a big old set. And an interesting property of the set of all sets is that it includes itself, right? Because it's also a set. We have also the set of all sets that include themselves, which is another one that will make your brain hurt. So the set of all sets does include itself. So it's included in the set of all sets that include themselves. And Russell's paradox, the set of all sets that don't include themselves. So for example, the set of Paul Irish doesn't include itself. It's just got Paul Irish in it. It doesn't have any other sets in it. Does Russell's set include itself? So does the set of all sets that don't include themselves include itself or not? And the answer is yes and no. Because as soon as it includes itself, you need to remove it from the set. But as soon as you remove it, you need to put it back into the set. So this, Bertrand Russell was trying to establish that mathematics worked really well and had a solid basis in set theory, and then this burned him. He kind of had a breakdown about this because he found this set that you just couldn't really deal with in a nice way. So there's paradoxes at the heart of set theory, and you just can't get away from that. So now we're going to deal with a much nicer set, one that's much easier to think about. It's the empty set. So all the sets that we've talked about so far have relied on external objects. We needed things elsewhere in the world or in the Platonic realm or something to put into the sets. So it's like the people in this room. We were relying on those to define what that set was. But there's an interesting set with no members, and it doesn't rely on anything. And that's called the empty set. So that's just the two curlies with nothing inside of it. So we can derive this set in various ways. It's easy to show people that the empty set exists. The set of Porsches that I own or will ever own is an empty set. The set of numbers that is less than 10 and greater than 20. Obviously, there's no number that is both less than 10 and greater than 20. So that is also an empty set. And we just think of that as being the empty set. In all of these cases, it's the same set, it's the empty set, it's a set with nothing in it. And we can use the empty set to produce numbers. That's why mathematicians and logicians like it. They can use the empty set as a basis for mathematics. So they can derive the number 3 from the cardinality of the set with three empty sets inside of it. So there's a set, inside it has 3 empty sets. I can produce the number 3. I can say, well, obviously the number 3 exists because it's the cardinality of this set, and it doesn't depend on anything else. All you need to say is that sets exist and the empty set exists, and we can get the number 3 out of it. So several formalizations of the foundations of mathematics, proofs that mathematics has a rigorous foundation, that we're actually talking about something and not just hallucinating. You can use this as a way of doing it. And lots of different formalizations have done that. So the surreal numbers I'm about to finally talk about are using this idea. They're using a variation of this idea. So we'll get on to those. So surreal numbers, they're not actually useful. Nobody would ever do this in real life, and I did it in real life, and I kind of regret it, but I get to talk to you about it now. It's from this area of recreational mathematics, which is also called armchair mathematics, or mathematical games, and Douglas Hofstadter called it metamagical themas, which for anagram fans is an anagram of mathematical games. So it's implicit in here that it's not of any particular use, it's just interesting to think about. And surreal numbers were invented by John Conway. And I picked this picture of him because he looks quite depraved in there. I kind of like that about him. And Harvey Birdman likes it too. You will have heard of Conway because you'll have heard of Conway's Game of Life, and this is not JavaScript, this is actually an animated GIF, so I'll leave that one on for a second for you to enjoy. But obviously, Conway is a time waster, right? He's interested in the Game of Life, which has no real practical usage, and he's interested in surreal numbers. So that's kind of his shtick, is like things that are interesting but don't matter. I first heard about surreal numbers from Donald Knuth, which makes it sound like I know him personally. I've never met the guy, but he's written a book about it. He's known as the author of The Art of Computer Programming, which I tell my students to read because it's currently 5 volumes long and about this wide, and no one will ever get to the bottom of it. Bill Gates once said that if anybody had actually read the whole thing, they should apply to him directly for a job. I don't know if he still says that, but he did. But Donald Knuth also wrote this book, Surreal Numbers. And I don't remember how I first heard about this book because I didn't know it was going to be a big deal to me, so I didn't make a note of it. He wrote this book in the 70s, and you'll see how 70s it is when I show you the subtitle, How 2 ex-students Turned On to Pure Mathematics and Found Total Happiness, which is very 70s. But also, if you enjoy the cover, which I believe his wife drew, that's 2 people sitting on a beach having a chat about surreal numbers. And that particular color scheme is also very, very 70s. It's not a good book. It's not written as a textbook. The whole thing is written as a dialogue between these 2 starstruck lovers sitting on this beach somewhere on the coast, and they just invent surreal numbers or discover surreal numbers as something to do. It's interesting if you're interested in surreal numbers, but I wouldn't go to it if you're looking at putting on a play for your local theatre company or something like that. So surreal numbers, this is how they work. Surreal numbers are made up of sets of other sets. So a surreal number is a set with some other sets inside of it. And we make new numbers by taking existing numbers and putting those in new sets. And in a second, you'll see how horrible the syntax for this is, the notation, but you should be able to get the idea of how it works. So each set has 2 members, what we call a left and a right. So this is what it looks like. This is the template for a surreal number. It's a set with 2 spaces in it, 2 slots in it, into which we're going to insert other sets or other surreal numbers. So to get things started, you have to define the first surreal number, and this is what it looks like. That's the number 0, and it's a set with 2 empty sets inside of it. So the left part of it is an empty set, and the right part of it is also an empty set. So that's a given. That's an axiom of the system. Once you've got that, we can make everything else work. So this is the number 1. What we do is we put, in the left-hand slot, we put the number 0, which we defined earlier. I've marked it in blue there, so you can see that it's just that same symbol again. And the right-hand side is just the empty set. And to make it a little bit more readable, we usually write it in that way. We write the number 0, meaning the surreal number which represents 0, which we've already defined. That goes in the left slot, and the empty set in the right. We also got -1, which we do the same thing. We put it into the right slot rather than the left slot. So here the left slot has the empty set in it, and the right slot has the number 0, which looks like that. And then this is where you can see how it starts to get hideous. This is the number 2, where we take the existing number 1 and put that into the left slot, and we leave the right slot alone, so it still has the empty set. And marked in blue in the middle there, you can still see the original 0. So we have a 0, and that's used to produce a 1, which then is used to produce a 2. And you'd write that in that syntax. You'd say the number that represents 1, the sets that represent 1 go in the left slot, and the empty set on the right. And -2, we do the same thing. I've left the left set alone, and I've put the number -1 in the right-hand set. Is that all perfectly clear? So you can also use this to produce fractions. So the fraction here, we take the number 0, put that in the left slot, and the number 1 goes in the right slot. You can produce a quarter by taking the half and sticking that in the right-hand side. And you can produce an 1/8 by taking a quarter and putting that in the right-hand side, and so on. And you can keep doing that to get successive powers of 2. So if you do this forever, what you actually produce, and people who are much smarter than me have proved that this is correct, you can get the entire continuum of real numbers. So that means all of the numbers that we're familiar with, the real numbers, are all going to have a space, a representation in this real number system. It might be, thousands and thousands of sets of empty sets, but it's possible. It can be done. And the surreal numbers have various interesting properties, which is why mathematicians are interested in them. So for example, the surreal numbers contains more numbers than our actual real number system. There's some bonus stuff that you get for free if you use this system. There's some numbers that you can express as surreal numbers that you can't express in any other way, and they still behave like numbers. You can still do all the usual mathematical stuff. One interesting example is you have different sizes for the number infinity. You don't just have positive infinity, you've got different sizes of infinity. And they're all infinite, but some of them are more infinite than others. No, seriously. So this is an image which should make it all perfectly clear to you. It's much too tiny to read, but this is from the Wikipedia article on surreal numbers. And it shows how you start from 0 and you keep producing more numbers in terms of the numbers you've already got. And you'll see down the bottom it gets very thick. It means we've filled out the number line. We've got all these numbers in there. So my stupid idea was to implement surreal numbers in JavaScript using empty arrays as empty sets and as few real numbers as possible. I wanted to see how far I could get without using any actual real numbers. Just trying to do the whole thing, bootstrapping it all off surreal numbers. So that's what 0 looks like. On the first day, Conway created 0, and that's our array with 2 empty arrays in it. And what would this mean if I got this working? Every real number could be represented, so we wouldn't have the limitations of current JavaScript numbers. You could go up as high as you wanted, you could go as low as you wanted, you could get very small numbers, all the fractions and everything would work properly. You wouldn't have the rounding errors that we saw before when we had 0.1 to 0.2. There's also no fear of underutilizing your memory. You don't, because these things are arrays of arrays, if you've got a MacBook with 8 gig of RAM in it, you can very easily exhaust that memory just by using fairly small numbers. And beyond that, there's no need to restart your browser periodically. Surreal numbers will do that for you by crashing the browser entirely. So if that's what you're looking for in a number system, this is a solution for you. So how far did I get with this? I've got natural numbers in there. That was a nice surprise to get that working. I can now, if I have very, very powerful machine, I can count up to infinity. I've got all the integers, so that means I can count down to -infinity. That works well also given infinite computer power. So in theory I can go up as high as positive infinity, but of course it will crash long before it gets there. I've managed to go from an integer, so I can take a normal human number and convert that into any surreal number. And I can go the other way, I can get the integer version back. And I've got equality working, which I'm quite pleased about. So I can say whether 2 surreal numbers are equal. I've also got the comparisons working. So I can say whether 2 numbers are less than or equal to, or greater than or equal to. That all worked really nicely. So some of the code, I was surprised by how beautiful this turned out to be. You probably can't read that especially well there, but what I've got is the is equal to. I define that by saying a number is equal to another number if it's both less than or equal to the other number and greater than or equal to the other number. If both of those conditions are true, if it's both less than or equal to and greater than or equal to, I know it must actually be equal to. So the test for equality is just that one single statement in that single function there. So that was a nice surprise. And the rest of the comparisons are really nice as well. I've got is less than is defined by saying it's not greater than or equal to. To work out if something is greater than or equal to, I just work out if it's the other way holds, that the other number is less than or equal to this number. And is greater than, it's just the same as the first case. I say if it's not less than or equal to. So that's all really nice. That's a very short amount of code. You'll see, though, that I've only got 3 of the comparisons in here, and you know that there are 4. And the reason I've put this on a separate slide, this is my beautiful code, this is my nightmare code. So to make all of this work, all the other ones I could define in terms of this one actually had to do some work to make it happen. And there's a whole bunch of code in there. I'm not proud of that stuff. It could probably be improved, but it gets crazy to work out which side of 0 you're on and how large numbers are. So if I'd known that was coming, I wouldn't have bothered with this and you wouldn't be hearing from me today. So the things I'd like to do, I haven't learned my lesson from this, I'm still doing this. I think the frustration I have is because I'm teaching at the moment, I'm not actually making anything new, so I'm just looking for random problems to solve. I'd like to get fractions working. They're in the book, but I haven't actually implemented them yet because that's going to mess up all of my existing code. I also have no arithmetic, so I can't actually add or multiply or divide any of these numbers yet. I can just make them exist and count with them, but that's all. So you can see this code for yourself. I've put it up on GitHub. My username on GitHub is coldhead, and it's SURREAL.js. There's no fancy test suites or anything like that. It's just my file with 170 lines of code that implements the SURREAL numbers. But what I would argue is that it's better to do this stuff yourself. I didn't make this library because somebody would be like, oh, that's good, I need an implementation of SURREAL numbers to do maths in JavaScript. It's more that it was highly educational and a lot of fun to do. And I would urge you to go and have a look at this book. It's freely available in various PDF forms. You can go and read it and have a crack at implementing it, or even just pushing these things around on pen and paper is satisfying. So I've got also here a short list of books if you're interested in any of this. This is the things I would suggest you read if you're interested in this topic. Douglas Hofstadter wrote a couple of books in the 70s. There's Gödel, Escher, Bach, and Eternal Golden Braid, which is about number theory and formal systems and whether computers will ever be able to think, that kind of thing. And he also has a series of essays called Metamagical Themas. Rudy Rucker is a computer scientist and mathematician who also took a lot of drugs and also wrote a lot of fiction. I particularly recommend his WARE tetralogy, which is software, wetware, freeware, and realware, which deals with artificial intelligence and robot rights and things like that, but also the hot topic of human-robot sex, which I know a lot more about now. And there's he's as an actual professor, he's written a couple of serious books. So there's a book called Mind Tools, which is about the fundamentals of mathematics and how it works, and another book called Infinity and the Mind, which is about, well, just what it says, really. I also really like David Foster Wallace's recent book, Everything and More, A Concise History of Infinity. So these are all pop books. They're not for mathematicians. They're for people like us who have some interest in these things. Everything and More is just a history of how mathematicians and logicians have grappled with infinity. I'm also recommending Alice in Wonderland with this cute quote from Alan Perlis. The best book on programming for the layman is Alice in Wonderland, but that's because it's the best book on anything for the layman. And if you don't agree with that, that just means you haven't read it enough times. So you should go and give that another shot. So what I learned about maths, I'll just quickly sum up with what I took away from all of this. Making maths work is actually really hard. You think that's easy, children can count, I'll be able to do this for sure, I've got a textbook to help me, and it's not like that. It actually turns out to be much trickier than I expected. Especially if you have to build your own numbers. So if you're not using any of JavaScript's numbers behind the scenes, if you're doing it all yourself, you'll appreciate how much is going on there. When you get it to work, it is incredibly satisfying. When you create a giant number, you've got an integer, and you say, give me the surreal number version of this, and then you say, what's the real number, the integer version of this, and get it back the other way. That is satisfying in a way I wasn't expecting. Particularly as it's not actually useful. It was just like, I've got this hard problem to solve, and then I fixed it. But what I especially have realized is you can't take your number implementation for granted. So if maths works in your programming language, that's really a big deal. People have put some hard work in there to make that happen for you. So if something works, you should hug an implementer. We have Dave here, if anyone wants hugs later. I don't know how he feels about that, but you can negotiate that with him. What I learned about programming. These particular problems, this is new stuff for me. I hadn't solved this particular problem before. And this involved an incredible amount of staring into the distance. Lots of walks around the harbor, just thinking about how the hell I'm going to get the next bit working. And it didn't look like I was working, but I was working really hard. The old-fashioned pen and paper approach goes a long way with these kinds of things. Where possible, it's good to get Angus Kroll from Twitter to review your code. He's available on Twitter, and I don't know, just ask him. Just send him your reviews. Maybe he'll do it. He did it for me. And finally, what I learned about the big stuff. It's good to break your habits and get out of your comfort zone. So as web developers, we're used to doing web stuff, and we tend to see everything in terms of DOM manipulations, or if we're Node developers, we think about streams all the time. It's good to just do something that isn't of use to or isn't necessarily part of your daily life, just as a mental exercise. And it's, people say don't reinvent the wheel. You can reinvent the wheel. You can make stranger wheels. You can make wheels that don't work as well as the existing wheel. The existing wheel is pretty good, but you can learn some interesting stuff by making bizarre new kind of alien wheels that nobody needs. But also, I got this nice sense that wonders never cease. So the more I've looked into the theory of mathematics and how it all works, the more surprised and kind of delighted I am. There's all this magical stuff that exists somewhere, I don't know how it works, and all these strange properties arise from it, like surreal numbers or whatever else you want to look into. But overall, I would argue for making beautiful and useless things just as something to do. It's immensely satisfying. It might not help you get a job, but do it for yourself. And that's all I've got. I won't be taking questions because I don't know the answers, but thank you very much.
If we can put our hands together for Joel again, and also a round of applause for Harvey Birdman, who was pivotal in that presentation.